In this segment, we're going to take a look at where the transverse shear stress model comes from. Our goal is to understand how the beam shear is distributed across the cross section. Here's our answer under some very limiting kinds of conditions. So let's go back here. Here's your sponge beam. It gets bent. When the moment is not uniform, that means we actually have shear presence. Remember, dm dx, the rate of change of the moment, is equal to the shear. So when the moment is not constant, then that's why you're going to end up getting then you have shear. Well, how is that shear distributed in the cross section, right? Here's the beam, here's the long axis, here's these red lines that represent the edge of the cross-sectional plane. Plane sections remain plane, homogeneous material, isotropic behavior, all these kinds of assumptions we had in sigma equals my over I development apply here too. Small deflection theory, all that kind of stuff. The cross-section we're referring to is, of course, this part here, right? So here's the centroidal axis, right? And there's the longitudinal axis, and those two together make up the neutral surface, or plane, right? Plane sections remain plane under bending. And we've got then this shear force that might be going on. So let's take another closer look here. Here's our moment at the left. It increases by some increment over here on the right, and that happens when you have shear, and that shear might also have some incremental change from the left to the right. Remember, the special calculus is, this isn't some just sort of magical thing, it's just very literal. It's the shear on the right is equal to whatever it was on the left, plus some incremental change as we walk across over a length that is dx, right? And that's, you know, some textbooks will do this as delta x and all this kind of stuff, but then they'll just take it as the limit. So I like to just sit here and go directly with the dx version. You're seeing the side of the beam right here, okay? So that's this side. We're not looking at the cross section, we're looking at the side of the beam. Right now, the weird thing here is, the question we're asking is, how is this shear force distributed across the cross section? And you might think it's, well, that's easy, that's V over A. Not a very good model. This is the model. V over A is actually pretty poor at handling the variation of the shear stress across the cross section. So it doesn't work very well to use a direct shear model. And the weird, truly weird thing here is that to look at this direction, we're going to look at the perpendicular direction. That's really weird, right? So go back to here. We've got this thing bent under bending, and what we're going to do is take a little slice out of the top of this thing. That's what this blue line, blue shaded area represents. Okay, so we have a bending stress here at the induced by the moment at the left compared to the moment over here at the right, right? The moment at the right is equal to the left plus some incremental change. And that normal stress will be given to us by the typical my over I model, right? So that means we do have to know, where's this neutral axis located, you know, somewhere, and then this y distance, that variation, that's our sigma equals my over I business. Okay. Again, this is not this is the side of the beam. The cross section comes out at, yeah, that's the edge of that. That's one of these little red lines we have right here, the sponge beam. Right? Same thing's true over here at the right. We've got sigma at the right, some variation of my over I. Right? Now that m here would be m sub l, and that m here would be m sub r. It's the same I, it's for the entire cross section. All right, so now let's see here. If the moments change, then the y's don't really change, but the i's don't change, but the moments do. Right? So wait a minute. These stresses aren't the same. There's going to be a difference here, and that difference is going to be this horizontal shear on the bottom of this little surface of this little piece that we have. That's pretty wild. Let's look at this even in greater depth, right? So on both sides of this drawing here, we're going to go up to a distance of y1 there. That's where we're starting at. Y there is just some generic location. And then out at this other one, up at the outer surface, that's that MC over I for the maximum, right? So this little y is running in between y1 and the C value. So let's look at longitudinal equilibrium. And we'll just take in some forces to the right in this longitudinal direction, right? So we'll have our H plus, these are in the same direction, so we'll integrate those over that area. These are going in the opposite direction, so subtract off the integration of those across that, and that's that little differential area that represents the real cross-sectional plane, not this blue area, but rather on that edge and then in and out of the plane of the paper. That's that top portion of the cross-section that we're dealing with. It's in static equilibrium, set it all equal to 0. Okay, so now what you do is say, all right, well, that means that therefore our H is equal, take this to the other side, we can represent it in the same integral, sigma r minus sigma L times dA, right? You don't add and subtract stresses, but you do add and subtract forces. Stress times the area turns it into a force, right? Okay, and where are we integrating, what area are we integrating that over? That's from Y1 to C. All right, now, oh, wait a minute, we can substitute in here. Now, oh, well, now that's interesting. So H, when we sub that in, and we can factor out the constants that aren't variable across that little area, which would be the moments in the second moment of area. And so that would be mr minus ml over I times the integral from y1 to c of y times dA. Now, technically it's y that's running for y1 to c, not the area. So that's a little calculus mistake, but conceptually that's what we're talking about. Right now, oh, wait a minute, y times dA, a distance from the neutral axis to some little area, that's just the first moment of an area. And we've got a special symbol for that. That special symbol is Q, right? It's defined to be this little first moment of area business. That's what's going on right now. That Q is mysterious to a whole lot of people. So we'll take a couple other little videos and examples. Just stick with it, follow through, just put that aside. We're just going to call that Q for now, a capital Q, and we'll come back to it and illustrate what's really happening here as we get later into some examples. Okay, so this is all just from equilibrium. Now, mr minus ml, well, that's just the difference between the moments on the left and the right, and that's going to be given to us by dm, or if you prefer, make it delta m. But now we get something even more special, because remember, the rate of change of the moment is dm dx equals v, or dm is equal to v times dx. Ooh, you know, that's kind of exciting stuff here. V times q over I times dx. I just split the v and the dx, because in our model, tau equal vq over ib, look what we've got, vq and the I, and we don't have the b in there, and we don't have the tau in there yet. Well, now let's take a look. This h is going to be spread out in an average sense over a surface area that's dx long, and then in and out of the plane would be this b, or the width of the cross section. Now that's kind of weird, I know, but, and you'll see it again in later on, but what we've got is h is the same thing as tau average times our b times our dx, the width of the cross section at y1, right? And that's going to be equal to vq over I times dx, and of course dx shows up twice, and lo and behold, we end up with tau average equals vq over ib. We usually drop the average. It's implied that you understand that that's the average across this width, and so on and so forth. Now, there's one more little piece that's kind of important here that we also need to talk about, because that's the horizontal shear stress. What does that have to do with, you know, on this plane? What does that have to do with going on vertically, right? So let's take a little tiny little piece right there, right? And what we've just found out You can do this on top or bottom, it doesn't really matter. But on the bottom here, we've got this little shear stress tau that we just learned how to calculate, right, or the model. For equilibrium in this direction here, those two have to be the same, tau times dA really, but it's a cube, so the surfaces all have the same little area, right? Well, that would want to spin this thing this way. So that means we have to have something going in the opposite direction, kind of like a force couple, and it's going to have the same value of tau because the area, again, it's a cube, so all the areas of the surface of the cube are the same. And so we're either going to have that set up, which is exactly what we've got set up over here, or we have to have the other one, which would be in the other direction, right? That those shear stresses tend to pinch, and either pinch in different directions. So pulling, elongating this way on this one, pulling, elongating the other way, and shortening in the opposite direction, which is exactly why we see those 45-degree kinds of cracks in that reinforced concrete model that we saw. It's weakest in that particular direction. We'll come back to that another time. But we have tau, tau, tau. So that's this little weird thing, this approach. We're going to look at the horizontal shear to get the vertical shear, which is what we really want. And because of that equilibrium of that tiny stress block, that all leads us to this as our variation of shear stress across the cross section. So there's more to that, and we'll look at that in some other companion videos.